Today, I'll talk about turbulence control experiment using distributed actuators, distributed sensors, and machine learning. So because my background is more on the experimental side, so I will present both the design, construction of these novel turbulence control experiment and also the application of the cutting edge machine learning algorithms. Okay, so let's start. So first we'll talk about the research background and motivation. So the flow separation control or the background of flow separation control is more on the transport vehicle side from in my research. So here I present like flow over an eVTOL. So this is a prototype of EHang 216, and I draw some schematics of the streamlines, and the flow goes to the rear part of these kind of eVTOLs, not only eVTOLs, but also maybe cars, trains. So there will be flow separation cost in the upper part of these transport vehicles. And in the academic research, we always use like simplified models to represent this type of flow separation over sudden expansion of the model. So in this case, we use like a backward facing ramp to investigate like not only the mechanism of flow separation, but also to demonstrate like flow control strategies for which are applicable to transport vehicles. So reducing flow separation is essentially very economically important for all kinds of transport vehicles, not only for ground vehicles, but also here, like for these newly emerging aero vehicles. So when the cruise speed is about 50 kilometers per hour, the aerodynamical drag will count for 50% of the overall drag, and thus for the ground vehicle, for aero vehicle, this number will increase a bit more. And for higher speeds, like here, I present the result from 130 kilometers per hour. The aerodynamical drag will be the major component of the overall drag. So that said, investigating and control the flow separation in these simplified models and also the actual transport vehicles is of great economic importance. And over the past like few decades, the flow control techniques has been developed like drastically. So here I present this review or overview of the flow control strategies. So in the previous flow control experiments or simulations, the flow control approaches can be divided into like two parts. One is passive, the other one is active control. So for passive control, examples includes like the use of riblets, vortex generators, in which the additional energy is not required for achieve like flow control results. And for active control, we need to input additional energy inside the flow control plant to achieve good flow control results. And for the previous research, the passive branch and active branch are more or less like independent, and there's no good way to include both control strategies at the same time. So in our research, we want to propose like the concept of hybrid actuator, or in the following, I will call it like multi-modal actuator, because it can use multiple modes to control the flow. So it can actually, or essentially in our idea concept, it should be able to operate under three modes. One is off, which means this novel multi-modal actuator will be flush with the wall where separation occurs. And number two, it should be able to operate under purely passive mode, which means this passive unit will only be activated and no extra energy investment is required. And essentially, finally, it should be able to, based on the passive results, operate under an active plus passive mode, which means there is additional active component can be activated to further improve the flow control result. And for the background of the from the control side, so I will talk about the evolution from one input, one output to multiple inputs, multiple outputs, and to our the concept we proposed, like distributed inputs, distributed outputs. So for single input, single output, like CISO, like this type of research has been conducted over the past, I don't know, 20, 30 years. And this is used, or nowadays, this CISO concept is used to develop new novel controllers. And currently in the industrial applications, the mainstream is more on the MIMO side. So by using order of 10 sensors and actuators, we can use this sensor input to effectively perform different flow control, or just in general control in different industrial and academic plants. And with the development of hardwares, I would say in more and more applications, people use more sensors and more actuators in the flow control problem, or in the problems related to flow dynamics. So here I give 3 examples. The first one is a total of 100 microphones in SHA, NASA, which is used to investigate the aeroacoustic characteristics of a jet flow. And in the second case, so this example is more about the actuators. So a total of 59 jaxos. So this is kind of a novel active actuators has been used to control the wake structures behind a blunt body. And for actually passive actuators, also a total of 30 passive vortex generators has been adopted in a concept car, which is Mercedes-Benz Avatar, to reduce drag and increase the actual flow efficiency, aerodynamical efficiency of the car. And so with these type of examples, we would say from the hardware side, we are ready to go into distributed inputs, distributed output scheme with the order of 100 sensors and actuators. But this dramatically increased number of actuators and sensors will pose a strong challenge to the control algorithm, because it is more difficult for the control algorithm to tackle this high dimensional and strongly nonlinear space. So here I give introduction of like so why we need actually machine learning control to solve the turbulence control problem. So for the plant model, this is just a dynamical model of the flow control plant, or any control plant. So A represents the state space. Oh, so this figure is from Noack and Brunton, 2016 annual review of fluid mechanics. And so here A is the state space, and B is the actuation, and S is the sensor signals. So we model this as a dynamical system. And so there are different ways to tackle the dynamical system control problem, depending on the linearity of the plant. But unfortunately, for most of the flow control problems, it is strongly nonlinear. and it is hard to model the flow control problems and get a very efficient flow control outcome. So for this strongly nonlinear problem, we need to use the tool of machine learning to actually solve the problems in an unsupervised manner. And this is more like a very advanced trial and error, and I will introduce it in the following slides. But so that is the introduction or the background of my research. So with this background, in this work, we designed the smart skin, which is a flow control plant or experimental plant containing distributed inputs and distributed outputs. And for this type of in the smart skin hardware, we adopt like very novel actuators which can execute both active and passive control commands to more efficiently obtain the good flow control result. And with this hardware, we can pose ourselves in a 60-dimensional control space. And in this high-dimensional space, we want to optimize the flow control strategy. So we use like the artificial intelligence or machine learning algorithm to optimize these flow control parameters and functions in a limited time horizon. And the results show that this machine learning based optimization is really efficient in finding a very good flow control outcome in the limited time. And yeah, so that's basically what I will present in the next sections. So here, to start with, I present like how this type of the smart skin is designed and how we implement into the actual wind tunnel model. So as I described before, the goal of this plant is to use distributed actuators and to perform separation control for flow over a smooth ramp. And also we implement both active and passive control for every actuator. So to achieve this, we use like this type of like red components. So for each component, it is actually a vortex generator. And for the passive control part, it is achieved by the stepper motors underneath. So with these stepper motors, what I can do is I can convert the rotation of the stepper motors into the height adjustment of these vortex generators, which means for each vortex generator, I can make the height adjustable. When the height is 0, so this element will be flush with the wall of the ramp, and when it actuates, it will be lifted up to arbitrary heights within a certain range. And to achieve active control, so because these actuators are made by 3D printing, so this allows me to make a built-in piping inside this component, inside this module, and we connect this tubing to the compressed air, and this will achieve a mini jet which is blowing in the streamwise direction. So with this combination of the stepper motor and like the tubing to the compressed air, and also like this 3D prototype component, 3D prototype vortex generators. So this makes a multi-module actuator. And what I did is I built this module and then, or several modules, and then lump it in the spanwise direction of the wind tunnel. So this makes 5 modules or 5 actuators in the streamwise direction and 6 modules in the spanwise direction. So with this type of arrangement, I deploy these multi-module actuators in a distributed manner. And this is for the actuators. For the sensors, we use pressure tabs to monitor the pressure on the wall of the ramp. So here for each actuator, it has 4 pressure tabs in the neighborhood, and all these pressure tabs are connected to a very high precision pressure scanner to acquire the wall pressure information. And so this is more on the ramp side. And in order to place it in the wind tunnel, we also generate or we also design a 4-body. So this part is more like airfoil shaped, and a boundary layer tripping device is also deployed to trigger the turbulence boundary layer, because turbulence boundary layer is more common in the transport vehicles. And so these are some of the relevant dimensions, and throughout this work, the free stream velocity is 7 meters per second. Okay, so that is more or less the CAD file, the CAD rendered image of the smart skin. And with this slide, I want to show you the actual how it actually looks like in the wind tunnel or in the lab. So basically, similar to the previous slide, just each of these yellow module represents a multi-module actuator, and it is distributed on the backward facing ramp in a distributed manner. And so this is just where the active control comes from, and this is just the passive actuators. And we connected to the solenoid valves. Like these high frequency valves is able to control the on-off state of the active actuators in a very timely manner. And the maximum frequency is about 300 Hertz, although in this work, we just use 100 Hertz to catch the dominant frequency of the flow. And with actuators, sensors, like all these type of hardware configurations, we are able to perform like flow control experiment. And our goal is to just minimize the cost function. And the cost function is related to the distribution of pressure recovery on the surface of this ramp. And we will discuss a bit more in the following slides. Okay, so this is actually just a movie of this plant, this smart skin plant. It just shows the on-off of these passive devices, and I use these papers to show like the active blowing capacity, or like the on and off of switching of this active blowing of all the actuators. So this gives you an idea how it actually looks like in the lab. Okay, so after talking about the hardware configurations, we want to use this very dedicatedly designed hardware to combine the hardware with the machine learning optimizers to perform very efficient flow control experiment. So here we use 2 different types of machine learning controllers. The first one is parameter optimization. So this is more on the open loop side, which means I will just turn the flow control problems into a parameter optimization problem. And with this, I use the particle swarm optimization. Like this is the cutting edge version proposed by Songqi and Noah in 2023. And just this improved PSO algorithm will provide a very efficient strategy to optimize the parameters in the very high dimensional space. And the second experiment we did is we treat this plant in a closed loop manner, and we want to optimize the feedback function of this plant. So with that, we adopt gradient enriched machine learning control proposed by Cornejo Maceda in 2021. to optimize like the feedback functions of this distributed input, distributed output problem. Okay, so with this kind of background or like the basic introduction of the smart skin plant, I will then show you the results. So first of all, I will show you the some parametric study results and also the aerodynamic characterization of this actual device. And then I will show you the results from the artificial intelligence control containing both open loop and the closed loop results. So as you saw just in the previous slide, we implement this device in open loop airfield type wind tunnel, and the test section of this wind tunnel is 25 centimeters times 25 centimeters times 60 centimeters, and we stick to a free stream velocity of 7 meters per second. And this wind tunnel is able to guarantee a turbulence level less than 0.7%. And for the stack height of the ramp, it is actually 50 millimeters, and this corresponds to a Reynolds number of about 23,000. And here I also provide the boundary layer thickness from different types using the hot wire measurements. And for the sensors, as I said before, so we connect all these pressure taps to a very high resolution pressure scanner, and this pressure scanner is directly connected to a real-time controller to achieve this feedback control under a very guaranteed feedback timed loop. And so here we need to parameterize like the passive control and active control in a mathematical manner. So for the passive control, we set or we convert this this control strategy to different VG heights between 0 to 8 millimeters, because 8 millimeters is really close to the boundary layer height. And for the active control, we actually control the on-off state of the mini jets driven by the compressed air and the solenoid valve. And for open loop control, we just make it a constantly open or constantly closed scheme. And for the closed loop control, we maintain a feedback frequency of 100 hertz. And yeah, as I said before, so to guarantee a very guaranteed timed loop, we use a real-time module from National Instrument to maintain a very precise feedback frequency. Okay, and mathematically, this turns into optimization problems. So our goal is to minimize the cost function. So here we use the cost function, which is related to the wall pressure distribution, and we want to maximize the wall pressure recovery on the pressure taps of the ramp. And to better visualize the optimization results, we also made a normalization of the cost function based on this equation. And we just measure the baseline cost function and divide the cost function created by any control strategy by this baseline value, and then use 1 minus this value to get a normalized cost function. So with this scheme, I want to make sure, or so what it did is to make sure that when this normalized cost function is less than 0, the flow control is effective than the baseline case for sure. And when it's greater than 0, it will be even worse than the baseline case. And this will be used in the parametric comparison. And also to monitor the relationship between the cost function and also the equivalent vortex generator height and duty cycle, we define JB star and JC star, which represents like the equivalent heights of each vortex generator, and also the equivalent duty cycle of the active component. And yeah, so first we will present the aerodynamical characterization of the force flow. So this is basically the hot wire measurements of the boundary layer and also the PIV measurements of the force flow on the center line. So from the hot wire measurements, we see a very typical turbulent boundary layer, and it matches well with the theoretical results and also the DNS results from old literature from 2010. So which justifies the experimental setup of this device is able to generate a very guaranteed turbulence boundary layer at the leading edge of the backward facing ramp. And on the right, I show the PIV measurement results from the force case, which means no actuator is activated, and we can all see the expansion of this shear layer and also the recirculation region at the bottom. And we also did the POD, the proper orthogonal decomposition, based on the velocity snapshots. So mode 1 represents the flapping motion of this recirculation bubble, and it is more like it won't convect. It won't be, so this structure won't be convected downstream along the streamway direction. However, for mode 2 and mode 3, so this is a pair of vertical structures, and all these type of turbulent structures will be convected downstream. And mode 1 will only just represents a flapping in the vertical direction. Okay, so here I show actually what we did is before adopting any machine learning algorithms, we did a very fully parametric study by specifying a range of different actuation patterns and evaluate the performance. So I need to explain the figure a bit because it's not only a bit full, but also a bit, the font size is a bit small. So so this is actually represent the activation pattern of the smart skin, and here we use only the passive. We use only the passive only mode, which means all these actuators are operated under the passive only mode, and no active component is allowed. So the red part means the corresponding actuators are lifted above the surface, and here there are 4 columns which represent the heights of all the activated actuators. So for example, one is 8 millimeters, which means all these red components are lifted up to 8 millimeters. And when it's 4, this means when the height is half of the maximum height, like 8 millimeters. And the vertical axis is the normalized cost function from the above mentioned definition. And again, when it's greater than 0, it means that the flow control is actually not effective. And only when the value is less than 0, so 0 here is the horizontal line here. Only if it's less than 0, it means the flow control is actually effective. So with this set of parametrical pattern and the corresponding evaluation, we see not all these parametric results will lead to a guaranteed effective, guaranteed and effective flow control result. So when the first row, like this span vector row, so this is span vector direction and stream vector direction. So when the first span vector row is operated along, it will always generate a worse flow control outcome. However, when the actuation starts with the second row, it will always lead to a guaranteed and improved flow field. So here we see for all different heights, the flow control actually gives a very improved flow control outcome, and also similar for this. So all these type of patterns will mean that it is really hard if you just operate under the or just perform trial and error. It is hard to really find a very guaranteed results from this parametric study. And the next thing we did is we also add active control on top of the passive patterns. So here I use like green dots on each actuator to represent the additional investment of the active control. And I mean, things becomes more complicated. So there are several things we need to notice. So this is the best results from the passive only case. However, when we activate additional active control on top of the passive results, we don't receive a guaranteed improvement of the flow field. So we see that the actual flow control outcome becomes worse than the standalone like passive results. So this means there are strong interaction between the passive component and the active component. And also, although the activation patterns are the same, like for this case, when the first two rows are active, for the minimum height, it will achieve a very guaranteed flow control improvement. However, when the height keep increasing, the flow control result becomes worse and worse. So these features, from these features, we really see a really complex search space, even in the simplified space, because in the current case, we only allow the same span-wise components to actuate in a very consistent manner or uniformly. So once we decide to lose this restriction and allow every component to move freely, it will go into a more complex search space and a very high dimensional space. So that means if we really want to get a very good, a very guaranteed flow control outcome, we really need the help of machine learning algorithms for fast optimization in a limited time. And okay, so the last thing we did for the parametric study is to visualize the cost function JA as well as the equivalent actuator height and also the equivalent duty cycles in a three-dimensional manner. And we can see a very clear Pareto front in this type of projections. So this purple point just represents a three-dimensional representation, and the ones on the side are just the two-dimensional projection of these cases. And for the best case here, so this is the best case and also the three projections, we see that the value of JB star and JC star are not the extreme values, which means if we invest more VG heights or increase more vortex generators, it will not necessarily improve the flow control outcome. And this principle is the same for the active control. So we can now just go to extreme values to find the best or the optimal flow control outcome with this plant. And as I said, this really needs the help of the machine learning optimizers. Okay, and some other observations is the median value of JA star is close to 0, which means if we just use like our randomly designed actuation patterns, the median value is close to 0, which means very insignificant flow control improvement. And this parametric study won't process very high efficiency. And also, as I said, without the assumption of uniform action in the same row, it is difficult to perform this type of parametric study and trial and error in this 60-dimensional space with only like the expert knowledge. And we really need the machine learning controllers to help us out. So in the next couple of slides, I will first introduce the smart skin separation control with particle swarm optimization. So here we use the cutting edge variant of the PSO. So I want to use this schematic to, so I don't want to present too much like math. So for the detailed implementation of this algorithm, please go to Shakurin and Nock 2023 publication for reference. But what it essentially did is just after a couple iterations, so this algorithm will just classify these particles or just so for each particle it represents one set of parameter, and yeah, so it will classify these particles and kill these hopeless particles and make it somewhere close to the current best solution, so such that it will have a stronger capacity to quickly find the optimal solution. So this is basically the similar schematic, but it would so because in the original publication it is posed in a maximization framework. So here all the algorithms and schematic is under the maximization framework, but with this targeted position mutated elitism, this algorithm can outperform other PSO variants by orders of magnitude. Okay, so now we go to the actual application of PSO TPME in the smart skin parameter optimization. So here the parameters we want to optimize is 3 passive parameters and 3 active parameters. So for passive parameters, we just specify different heights of the vortex of each vortex generator. And for active part, as I said, we only use open loop control, and we only specify the on-off state of each actuator throughout the experiment. And regarding the parameter setup of the PSO TPME algorithm, we use 35 particles, which represents about 55% of the overall parameters, and 1,000 iterations throughout the training. And to evaluate like or to avoid the extreme events during the training, we performed a total of 5 training or experimental campaigns. And this is basically the learning curve I obtained from the iterative training. So this shaded area represents just the envelope of all the 5 training cases, and the right line represents the one with the best solution. And so the green line here represents the case where we have the best parametric case with passive only actuation. And the blue line here represents the cost function where we use the parametric study to enable both active and passive actuations. So about 50 iterations for all these, for each cases, we can see that the optimization based on PSO TPME can already exceed the parametric best from the previous research, and it will keep going down after the 50th iteration, and drops down a very significant value of minus 1.477 after all this training period. And so this means in the finite time horizon, this algorithm based on machine learning can really beat the parametrical patterns, and yeah, really leads to a very significant flow control outcome. And when we visualize the actual pattern of the control, like both active and passive pattern, we visualize it here, and we use red, and we use red color to represent the actual height and activation status of each unit, and we use these green dots to represent the activation of the active control. So actually, in finite time, we see that this algorithm can outperform all these parametric results, but it looks like this pattern is a bit complicated, and it doesn't possess any perfect symmetry, although it's very efficient. And the control principle related to this actuation pattern requires further analysis and investigation. So to this end, we perform the PIV measurements on different cross-stream locations just to compare it with the force flow. So on different span-wise locations in the force flow, we can all see like the very significant, a very large recirculation and separation region for flow over the backward facing ramp. And I use a right line to just connect the vortex core at each span-wise location, and so this gives you a sense of how the flow separation actually takes place in this ramp plant. And with the flow control pattern from the machine learning optimizer, we see like the PSO TPME, and we see that like a very reduced recirculation, and so from the PIV results. And for some of the cases, you don't see recirculation, and in some of the cases, you see very little recirculation occurs inside this or on these span-wise planes. So I cannot get very good flow control outcome on the sides, because on the sides, the plant only have one side actuation, and we also have very strong like wall effect on the two sides. But besides the two sides, the resulting actuation pad, the resulting flow control outcome is very impressive. And so this demonstrates the effectiveness of the parametrical optimization based on PSO TPME. And we also want to, at the same time, we also want to discuss more about this training data, because as we said, so we generate really a lot of training data during the experiment, and how can we keep using, or how can we exploit more from this training data will be the thing we discuss next. So first of all, the first thing we can do is to visualize the control landscape of these individuals. So we have 3,500 individuals, and we can just calculate the distance between each individual and calculate the two-dimensional projection or distance projection of the individuals. So we call this control landscape or proximity map. And what we can see here is, so this looks very like a diamond, and for each small patch, the value goes really different from the neighborhood. So this not only demonstrates a lot of local minima, but also demonstrate the strong non-convexity of this flow control problem. And when we try to project a very complex landscape with a lot of minimum and a lot of minimum on this two-dimensional plane, so it will just generate this diamond shape, and even the particles are in two-dimensional sense very close to each other. It will generate a completely different flow control outcome. And in our lab, so we are developing a technique called topology assisted optimization to better analyze this control landscape and extract the local minimum and global minimum. So please refer to this newly published Physics of Fluid article if you are interested in this type of technique. And similarly, we also discussed the relationship between the cost function and also the equivalent actuator height and equivalent duty cycles. So in this case, different from the parametric study, we see the median value from the training data is about minus 0.5, which means this is absolutely more effective than the parametric study. And again, we don't see a convergence of GB star and GC star to the extreme values, which means not necessarily employing more actuators and more active controllers will lead to a better flow control outcome. And this again demonstrates the complexity of these type of flow control problems. And so again, this all these type of discussions demonstrate the fast and effective learning from the machine learning optimizer. And the last thing I want to discuss from this training data is feature selection. So because previously we get a very complex flow control pattern, and this is not symmetrical, and so what we want to do is we want to use this data to kind of features from this pattern, and then get a more interpretable outcome, which demonstrates still the efficiency of flow control. So what we did is we built a surrogate model based on the 3,500 cases of training data, and performed the feature analysis based on the model. And in this case, we just use the simplest randomized and perform the feature analysis. And because trivial features will not have very significant effect on the model accuracy, and remove these features will not improve, will not influence the loss function when we fit the model. So we just start to remove like the trivial features one by one, and we find that after removing 40 features, we can get a very quickly increment of this model fitting loss, which means the features from 40 to 60 will actually dominate the description between the input features and the loss function. So what we did is we preserved these important features and enforced symmetry. And this is what we got, a very interpretable pattern, because the flowing of the first row at the minimum height is consistent to the passive control result. Like for each case, if we only enable the first row and let it to blow at the minimum height, yeah, we'll always lead to a very guaranteed flow control outcome. So we can see with this type of feature selection and rearrangement techniques, we can really get a very interpretable and robust solution. And then I want to show some another case, like the closed loop control experiment using GMLC. So this is just feedback control using the smart scan. And here I show the schematic of the controller, the gradient enriched machine learning control. So this is basically based on the genetic programming. And the one more thing I did based on the genetic programming is to perform the downhill simplex for the good particles or for the good individuals. So I'll give you an example. So let's say this dot represents a good solution, and this is another good solution. So the combination of these two solutions will definitely lead to, or will have very high probability to generate a more guaranteed solution. So in this manner, it enriched the genetic programming using a gradient method, and so details can be found in Cornelo Maceda's GFM 2021. And so I'll just show you the final training results. So different from what we thought before, so this visualizes the duty cycle of each actuator. So we see like a very, or we cannot observe a very strong like feedback pattern. We can only see like fully open or partially. This is partially open is already very random or very few individuals, and fully closed individuals. So we think this is related to the hardware design, because the active actuation for the active actuation, the activation speed is already about 3 times of the free stream speed. So this might just break the feedback loop. But regardless of these discussions, so even for this a very high energetic activations, we can still get a very promising results from this closed loop control. And so this is just visualization from PIV, and the machine learning controllers can already provide a very guaranteed attenuation of this recirculation region. And so this is also a comparison of the POD modes for the original case and fourth case, just similar to my previous description, just flapping recirculation region and then the convective coherent structures. But after we exert flow control, active flow control, we don't see very large structures related to the shear layers and also the recirculation regions. You can only see these smaller structures, which is related to the mode from the mini jet actuators. Okay, and so with this, I will just make a conclusion. And so what I present in this seminar is the development and some experimental results of the smart skin. So it is an experimental separation control plant featuring distributed input and distributed output. And in this experiment, we employ state-of-the-art AI control algorithms to optimize the wall pressure recovery on the ramp. And we performed a series of parametric studies to not only demonstrate the effectiveness of the smart skin, but also it indicates a very complex control landscape. And when we use PSO TPME to optimize the control parameters, it finds a very complex actuation pattern inside from the 60-dimensional control space. And this combines both active and active control strategies. And for the closed loop control, it finds the optimum active control law, also in a finite time horizon, and lead to a very guaranteed reduction of the recirculation area. And in the future work, we will concentrate on the spatial temporal measurements and estimation of the flow field under this optimized flow control strategies, not only for open loop, but also for the closed loop control. So with this, I'd like to take your questions.
Yeah, thanks for Songqi for his like super like impressive like presentation. Actually, like I'm quite impressed. Like you finish all these like it's such a systematic work, but like you finish in 2 years, so it's super progressive, very amazing. So if you have any questions, you can just open your mic, or you can like type it in the chat as well. Okay, essentially I have a question like say, like you use like the passive and the active control, like it's sort of like the passive control like how to say a vortex generator. Like but like say like it's sort of like I saw you increase the height of the vortex generator, but like how can you like justice like some kind of like extra drag, or like something like as you like increase like maybe the power input when you increase like sort of it's more like a passive control thing. Like do you think like it's like zero, like it's sort of like only use passive control, this is a cost-free control?
Thank you, Professor Zhang. This is a very good question. So this is also something I didn't really stress out during my talk. So all this type of thing, all the reason we made this plant is to demonstrate the capacity of the idea. So the idea is for the future flow control with machine learning, we don't really need to take too much care of the physics. So let's say in this way. So what we just need is to deploy the actuators in the possible space. Like just in this case, we deploy the actuators everywhere on the ramp, and then use machine learning optimizers to decide which actuators should be enabled, which one should be at which height, and which one should be closed. And after that, just the last thing we do will be the application of different flow control measurements to interpret these machine learning optimization results. And what you said is right. The application or the use of the vortex generators, in this case, it might generate additional drag based on the shape of these vortex generators. But this is only, because this is only an academic research, and we want to sell or we want to integrate the idea of multi-module actuators, which means we want an actuator to perform both active and passive control. So in this case, this is the the only or the very let's say applicable design in the laboratory scaled experiment, and in the actual industrial applications, we will have more advanced equipment, more advanced prototyping techniques. So we don't really need to take care to really care about the additional drag caused by this this type of vortex generators, and by that time or people can design more dedicated actuators to solve the problem. And this is not the main focus of my research. My research is more on the principle side, like to demonstrate the applicability of this distributed input, distributed output system, and yeah, again, because it's a very academic research, I don't have a very good way to evaluate the actual energy input from this active actuators, because there are a huge energy loss during the piping. So we just use like the Pareto method to balance the different cost components, although it's not taken into consideration in this work. But yeah, if you want to really the active energy input, just use the Pareto method to determine a very gamma.
Yeah, Songqi. I think you're like you have some line block on your side. But anyway, it's sort of like we are about the time. We're about the time. Essentially, we actually like extra like 7 minutes, but usually we don't care. Like even we extra 10 minutes, we don't care. However, if anyone has any question, we can take one more question. Like, if anyone has any question? If no, I would like thanks everyone for participating like tonight's IBiM talk, and thanks for Songqi for your presentation, for sharing your work. Okay, so we'll see you next week. Bye, everyone.
Thank you. Bye.